Chapter 2, Section 2 is about using second derivatives to find max and min values and to help you sketch your graphs. First, before we talk about that, we need to talk about concavity, and concavity is the direction in which your graph is cupped. So if your graph is cupped up, then you're concave up. And your graph is cupped down, then you are considered to be concave down. So suppose that we have a function f whose derivative f double prime exists on some interval, an open interval. Then your graph will be concave up if you evaluate all those x values on that interval in your second derivative and they're positive. You're going to be concave down if you evaluate the x values on the interval and they are negative. So then your test for concavity would be to put in values in your second derivative and observe the sign, positive concave up, negative concave down. So rather than guessing where the place we would change would be, we could actually do something similar to that first derivative test where find where f double prime is equal to 0 or doesn't exist. That's going to be your boundaries, and then you're going to test to the left, right, and if you have multiple ones in between. Okay, so then let's go ahead and we're going to figure out where we're concave up, where we're concave down on this function, which is 2x squared minus x to the fourth. So we need the second derivative. So we'll get the first derivative. Derivative of 2x squared will be 4x. Derivative of x to the fourth will be 4x cubed, so it'll be minus 4x cubed. From there, we need to get the second derivative. Derivative of 4x is 4. Derivative of negative 4x cubed will be negative 12x squared. Let's set that equal to 0. Now this, we have a GCF, but it's not going to help us factor what's going to be left inside the parentheses. So let's go ahead and add 12x squared to both sides. And then divide by 12. This will reduce to 1/3. Take the square root of both sides. When you do that, you have to account for the positive and negative square roots, because if you square a positive square root of 1/3 or a negative square root of 1/3, it's still going to be 1/3. Okay, we're going to put these on the number line. Okay, I need an approximate value so I can figure out what my points are. Well, I know I can pick 0, it definitely will be in between. But if you throw this into the calculator, this is approximately 0.58, which means we can pick a negative 1 on this side and a positive 1 on that side for test points. So let's go ahead and put these test points into our second derivative. So f double prime of negative 1 will be equal to 4 minus 12 times negative 1 squared, which will be negative 8. So if you're negative, that means you're going to be concave down. We evaluate for 0. F double prime of 0 will be 4 minus 12 times 0 squared, which is 4. So that's positive here, so we're concave up on this interval. And our last test point's a positive 1. 4 minus 12 times 1 squared is going to be negative 8 again, which means we will be concave down on this interval. Okay, so let's go ahead and state our intervals. Again, these are open intervals. At the place of change, you're neither concave up nor concave down. So we're going to be concave up between negative square root of 1/3, positive square root of 1/3, and we are going to be concave down from negative infinity to negative square root of 1/3. and positive square root of 1/3 to infinity. So that little change in concavity would look something like this. So on this side, I would be considered concave up, and on that side, it would be considered concave down. All right, let's talk about the second derivative test for relative extremas. So suppose you're differentiable for every x in some open interval from the number a to the number b, and there's a critical value that you got from your first derivative, and that'll be number c, happens to fall between a and b, for which this says the first derivative is equal to 0, that's why it's a critical number. Then if your f of c is a relative minimum value, that means if I put c in my second derivative and it's positive, it's concave up. That's why it would be a minimum value. And then if I put that c into my second derivative and it's negative, that would mean it would be concave down, which means it's a relative max there. For your second derivative at c is equal to 0, that just means your test is inconclusive, and go back to your first derivative test. Okay, let's find the relative extrema and classify them as max or min using the second derivative test. So first derivative to get the critical values. So dy dx will be equal to 0 minus 2x. Minus 2x is equal to 0 if x is equal to 0. So we have one critical number. And we're going to get our second derivative. So d squared y over dx squared will be equal to derivative of negative 2x is just negative 2. This means your entire graph will be concave down. It doesn't matter what x is. So therefore, at x is equal to 0, since you're concave down, you're going to have a relative max. Remember, relative and local, those are interchangeable words. Some books use relative, some books use local. It doesn't matter which one you use. Okay, let's talk about the second one. First derivative will give us our critical values. So dy dx, 3x squared minus 12 plus 0. And we're going to set this equal to 0. Let's go ahead and factor out a 3. X squared minus 4 is difference of two perfect squares. So product of a sum and a difference of the same values. Which means, of the same values is 2. Which means critical value is going to be x is equal to negative 2 from that factor and positive 2 from that factor. So let's go ahead and get the second derivative. D squared y over dx squared will be equal to 6x plus 0, so it's just going to be 6x. So when we evaluate this at negative 2, it'll be negative 12, which means you're going to be concave down. Therefore, you have a relative max at x equals negative 2. And if we wanted to find these max-min values, we'd have to plug these numbers, these x values, back into our original function, but we haven't been asked to do that. We're going to evaluate our second derivative for x equals positive 2. 6 times positive 2 is positive 12, which means you're concave up. So therefore, for concave up, we're going to have a relative min. Okay, problems like these can be found on page 217.